So Grothendieck defined the notion of étendue as a topos that is locally of the kind defined by a post set of open regions, and it turned out that an étendue is always obtained if more generally we start with a category, a site, which as a category consists only of monomorphisms. If every map is invertible, i.e. a groupoid, then of course everything is a monomorphism. On the other hand, in a post set, everything is trivially a monomorphism, so that's obviously a generalization. It takes a few minutes to realize that such a thing is locally, in the appropriate sense, a post set. And so, but then conversely, it turned out that any Grothendieck topos, which is locally like the sheaves on a post set of regions, does in fact have a site which consists of monomorphisms. Okay. But on the other hand, one has to keep in mind that these so-called generalized spaces are not just the topos of sheaves on them, no more than the lattice of open regions itself determines the space. Because if it's a smooth space, or an analytic space, or an algebraic space, and so on, there is, in addition to the post set of regions, there is always the sheaf of local rings. That's why one talks about ring toposes, and it's absolutely essential that you have this kind of topos, this kind of topos, together with a ring object in it, or you lose completely the connection. The product, for example, with the pure topos is not the same as the product in the category pairs consisting of toposes equipped with rings. So, in particular, I mean, that's a simple example of that. The spectrum of a ring is not a topological space. It's not the Zariski. People study that space, but it's really only just in a very poor way connected with the scheme, because at least as essential as the sheaf of local rings. So when one pushes the picture down to a single space in that way, an additional structure is created which has to be carried along with it. So the sheaf of holomorphic or smooth functions, which of course is incorporated in the linearized theory, provided we construe it as being a monoidal abelian category and so on. But the fact that the product of underlying toposes or underlying topological spaces is quite different from the product of schemes means that an algebraic group is not a topological group. There is no underlying topological group for an algebraic group, just because the notion of group depends on the notion of Cartesian product, and that's not preserved by this forgetting process. So, I think, by the way, that in the case of algebraic geometry, that mismatch can be considerably alleviated if one considers that the base topos is not, after all, abstract sets, but rather the Galoisian topos of sheaves on the category of finite field extensions, which reduces to abstract sets only in case the ground field is already algebraically closed. Because by working in that which is a Boolean topos, working in that Boolean topos instead of an abstract set, one gets a much better match with the geometry. That remark, elaborating that remark, you see, is really only a fragment of a task which category theorists have been avoiding for too long. That's the task of the refoundation of algebraic geometry, taking into account the most up-to-date insights from category theory, based, of course, ultimately on Grothendieck's pioneering work, but not stuck in the archaic formulations that it was given. Grothendieck's formulation, the despite the last 50 years of work by algebraic geometers, has not been much developed. It's only been applied in its original formulation, something approximately its original formulation. And so it's long overdue for clarification. And this remark of mine that the basic ground topos, basic foundation, if you like, should not be Cantorian sets, but Galoisian sets. This is just the beginning of a fragment of that. Now, already in the 1950s, the first topos to be considered explicitly as a category was simplicial sets. In 1950, actually. Simplicial sets were introduced as a category. It happens to be a topos. It has many properties as a topos, which again, there's a long overdue task to explain not only is it a topos, but what are the special properties qua topos that it has. Because the homotopy theorists who work with it don't know these properties, they just use them. They're unconscious. In any case, when it was first introduced, it's interesting to look at this paper by Eilenberg and Zilber, because the first line of the paper says, you have to understand that these are like spaces, but they don't live on their points. Words to that effect. They don't live on their points. This was in spite of that, for years afterwards, people continued to think that spaces should live on their points somehow. Just completely should have been considered overthrown at that point. Not just for combinatorial spaces, but for all kinds. Slowly. Even more strongly, Grothendieck's 1960 techniques for construction of analytic spaces heralded the realization that categories of space need objects, i.e. spaces, for which any description as a topological space plus something else was awkward if not imprecise. In the ensuing half-century, simplicial sets have been extensively studied by algebraic topologists, led by Kahn, but the category theorists have developed only in a rudimentary degree the precise distinguishing features that simplicial sets have qua topos. Perhaps I should report here that finally, after 50 years, I met Kahn last month, Daniel Kahn. He doesn't go to meetings. He told me that he has worked for 50 years and more on nothing but combinatorial homotopy. This is his strength, that he doesn't let himself be distracted by other questions. But he just, I mean, it was just 50 years ago this year that his paper on adjoint functors was published, and it's had a tremendous effect. Certainly influenced my work a lot. Probably everybody's work, even the work of logicians. So he told me the story about how how the adjoints came about, which is kind of interesting, perhaps. First of all, Kahn himself is from Holland. He's a good friend of Ike Mertijk, for example, and I didn't know that. But his entire graduate career consisted of 2 months. He was working in Israel. Kahn was working in Israel. And Eilenberg stayed for 2 months in a hotel in Jerusalem. Kahn was already independently interested in combinatorial homotopy. So he went and talked to Eilenberg about it, and Eilenberg gave him a problem. He went home and solved the problem, came back, had another problem, blah, blah. So after two months, he had enough for a thesis. So then he applied to graduate school and entered the PhD program, translated the thesis into Hebrew, which was, necessary, and then got his degree. So this was his entire graduate career, was those few minutes were required to translate the thesis. He applied and got admitted, and anyway. So, but then he came as a postdoctoral fellow, or whatever they called it then, to Columbia, where Eilenberg was. And one day Eilenberg and Kahn and also Abhyankar, algebraic geometer, were discussing various things, and Eilenberg remarked that the tensor product functor is determined by the Hom functor up to isomorphism. Given the Hom functor, then there could only be one tensor product functor. Whereupon Abhyankar said, I wonder if the converse is true as well, that the Hom is determined by the tensor. Whereupon Eilenberg said, of course not. That's ridiculous. How can you say a thing like that? Which made Kahn so mad he went home and discovered adjoint functors. So one shouldn't be too fast. Well, no, maybe one should be fast, because it makes people mad and sets them in motion. And of course, the word adjoint was put onto it by Eilenberg. Again, there's a persistent mythology to the effect that the notion of adjoint functor is modeled on adjoint operators in Hilbert space theory, that sort of thing. Kahn says, absolutely not. He didn't even know what an adjoint operator was in those days. Just as I was saying, his actual mathematical education was rather narrow. Of course, he eventually learned all kinds of things, but at that moment he didn't know, never heard of adjoint. It was just, with Eilenberg, who saw some analogy. Okay, well, to come back then to the generalized space, no doubt the most important example of a topos which, together with the needed linearizer heap of rings, or whatever you want to put together, the example of a topos which is treated as a generalized space is the étale topos of a given scheme in algebraic geometry. This is something that's not needed in analytic geometry or C-smooth geometry, because in those two cases you have the implicit function theorem, and you can just talk about local homeomorphisms. But in algebraic geometry you do not have implicit function theorem. In other words, just because the derivative of a map is invertible does not mean you can even, square root is not an algebraic polynomial function, even though it should be invertible, locally invertible, not globally, as we're just talking about local. So the local homeomorphism condition in algebraic geometry was too strong due to the lack of implicit function theorem. But there is an infinitesimal analog, namely, as I said, that the derivative at each point, which is a linear transformation, should be an invertible linear transformation. So Grothendieck said, well, in algebraic geometry, let's consider the objects over a base that is equipped with a map to a base, but the map has this property of being infinitesimally invertible, but not necessarily locally.